you if you want to learn it or not. But I suggest you learn. So now we have this piecewise function f of t, which if you plot it, it has this shape. So it is 0 for t smaller than 0. It is t function for the range of 0 to 1. And then it has the value of 1 for range of 1 to 3. It has the value of this polynomial function, t minus 4 to the power of 2, for this range and 0 here. And you want to find the Laplace transformation of this. You can use the Laplace definition, and then for the different range, do the integration, which is very time consuming. And if you look at the table 7.2 and 7.3, you cannot find a f there which has this shape or this structure. So you cannot directly use tables. However, if you write this function in another way, then at some point, which I will explain or show you here in a while, then you can use this second shift theorem from tables to find the Laplace. So that's the point of all this second shift theorem, such that you can use it for finding the Laplace of the functions like this one, piecewise functions, which are not in the tables. So the first step, always and always, is to write, so I write it as the first step. So write or rewrite your function in the form of Heaviside function. Or actually Heaviside comes from Maple. This is a term which in Maple they use it for a unit step function. So if I can rewrite the function I have in a form of unit step function, then later on I can use this shift theorem. Well, let's see how can I do. So f of t would be equals to 0 for the negative range of t. So it is 0, we don't need to do anything, so I will just ignore it. I go to the next range, which is t, but this t, it is for a specific interval, it's not for the whole. Because if I write it, just again here just to show you or clarify, if I write it as a t and I want to plot it for, of course, t greater than 0, it will be this one, and it goes forever. But here, I should stay or keep it in a range of 0 to 1. This is a place when this shifting of u of t minus t0 comes in hand. I can write it as a t times multiply by u of t minus initial of your interval, which in this case is 0, minus u of t minus the second or the end of interval, which in this case is 1. Now I'm sure that my t will stay in the range of 0 to 1 only. So you could see I only stayed in the range of 0 to 1. And this is 1. I mean, if you plot this like what I did there, it has the value of 1 for this range. And if you multiply t by 1, it is still t. So this is for the first part, for the first interval. We do exactly the same approach for the rest. The next interval is from 1 to 3, and it has the value of 1. So I can write it plus 1 times, again, I need to specify the interval with the unit step function. So it will become u of t minus initial of the interval, which is 1, minus u of t minus end of the interval, which in this case is 3. So stay, I'm in the range of 1 and 3 only. Now the fourth row, I have plus t minus 4 to the power of 2, then multiply by, I can erase this now, and from here I go down, multiply by u of, again, beginning of interval, which is 3, minus u of t minus 4, and the last one is 0, so again, we don't need to consider or do anything, it's 0. Because 0 multiplied by anything is 0. Now, I have my function as a heavy side or in the form of unit step function. What I do, or what I suggest that we do now, is do the multiplication of the parentheses with the outside of the parentheses. So I write it as a f of t equals to t times u of t minus t times u of t minus 1. Just multiplication of this. This is 1, so nothing will be changed here. And now I need to multiply this by here. Okay. Are you all agree with me? Could you follow what I did? I just did the multiplication. Now I need to go to another board. 6. I need this one. Okay. When you are here, you should look at to the all terms you have, and if you have one term which is repeated in different places, then you need to do the factorization of it. So what I mean by that, you can see I have u of t minus 1 here and here. So I can make the factorization for these two terms, for u of t minus 1. For u of t minus 3, I have it here and here. So again, I can do the factorization. So again, I write my f of t. T times u of t. Then I want to make the factorization of u of t minus 1. If I do that, it is minus t plus 1. Okay, I will back to it. What does it? Just I did the factorization here. Then plus u of t minus 3. If I do the factorization, it is minus 1 plus t minus 4 to the power of 2 minus Again, any question for this step? If it's not clear, just ask, because if you don't get it now, later on it will become much more confusing. Yes, please.
I can't see the end of the blackboard.
Maybe I should. This is.
Yeah, from there I cannot see.
Can you see this one?
Yeah.
Then multiply by u of t minus 4.
Perfect.
This is here.
Yeah.
I just rewrote this stuff. Okay. here, when I want to do the Laplace, I want to use this second shift theorem. Let's look at the shift theorem. We had it. The important thing about this shift theorem, second shift theorem, is that in order to use it, your function, this t minus t0, should be exactly the same as this, what you have in the parentheses of u you have in front. So it has to have this t minus t0, it should be the same for both. Let's look at here. I have t times u of t. We can say that it is t minus 0 and t minus 0 because 0 is 0. Then, of course, both of them are the same, so I'm happy with it. But now let's look at the second term. Here I have u of t minus 1. So in order to use this theorem, I have to rewrite this. Of course, we should do it in a way that makes sense. But I have to rewrite it in a way that this becomes t minus 1 as well. What I suggest to do here is I write it as t minus 1, then I make the factorization of 1 minus out of parentheses. So you can see, instead of this, I use minus t minus 1. Now, I have exactly the same in the parentheses of u and what I have out. So now I can use the theorem. Yes, please.
So you took the intervals before, put it in put it all together in a long equation. You factor this.
Yeah, I did the factorization in a term which is possible.
Yeah.
And then I look at each individual term to see if it has this structure that what you have in front of you, you should have exactly the same format outside for the f as well, for your function as well. And here I don't have it because this is t minus 1, this is minus t plus 1, they are different. And in order to make it the same, I said I will make the factorization of 1 minus 1 or minus out of parentheses. Then now I can use this second shift theorem for this one as well. Let's jump for this for now. Let's look at the last one. Here is t minus 4, and I have t minus 4 here as well, so I don't need to do any work here. I can use the shift theorem, so that's good. But now let's look at here. So I only look at this term now and see if I can do any change here. Let me check my work. Okay. So now I have t minus 4 to the power of 2 minus 1. It comes from here. I should rewrite it in a way that I get the t minus 3 format. Why t minus 3 format? Because this is the expression I have in the u parenthesis. So I have to rewrite it in a way that this u of t minus 3, not u of t minus 3 is there. So I want to rewrite it in a way that I have t minus 3 multiplied by something. But I have to find this in a way that when I multiply by t minus 3, it's equivalent to the expression I have. Here you can use maple, for instance, for u or for this purpose. And I think it will become t minus 5. So if we do the math, we can check it. So this is t2 minus 5t minus 3t plus 15. So it is t2 minus 8t plus 15. And here if I expand this, it is t2 plus 16 minus 8t minus 1. Am I right? Yes. So t2 minus plus 15 minus 8t. So you can see they are exactly the same. So again, for this step, you can use maybe. Where is the eraser?
Under your paper.
Oh, okay, thank you. So I just show you this that they are the same. And again, maybe you ask how you know it should be t minus 3, because I looked at the parentheses I have here. So now, instead of this coefficient, I can use this one. So I can write it as t minus 3 times t minus 5 times u of t minus 3. I multiply this u with inside the parentheses t minus 3. It will become t minus 3 u of t minus 3. Then let me check if I'm doing everything correctly. Oh no, before multiplication, maybe it's good to do something else. So now, for t minus 5, another thing I can do, I can write this for this one. I want to get rid of it, so I can write it as this format. Why I do that? Because I want to have t minus 3 and not t minus 5. So that's why I do t minus 3 minus 2. Okay? So now I can rewrite everything again. I have f of t, which is t times u of t, minus t minus 1 u of t minus 1. And now t minus 3 times t minus 3 minus 2 times the u. Which is t minus 3 to the power of 2, because I multiply this with this one, minus 2 times t minus 3 u of t minus 3. What I did, I just multiplied this purple with the blue. And then minus now I multiply u with the parentheses. Now all the terms we have, it's in a way or in a shape that I can use the second shift theorem for it to obtain the Laplace. I know that doing these tricks or rewriting is not always easy, or it takes time to come in mind what should I do here, but you have to practice for different examples and hopefully it will become easier. And because finding these ways is challenging, I like to have it in always exam tests as well, so I can test the students. But any questions so far? Because we are not done yet. Yes.
When you make the u in between two parentheses, does that mean that both parentheses are multiplied by u?
You mean here?
Maybe a little bit further down, like the last one.
Here, yes, you can see I have this big parenthesis. I mean, I open it here and close it here, multiplied by u. So it means u should be multiplied with all the terms I have in this parenthesis.
Okay.
So, you know, this parenthesis is for the first term, and this is for the second, and this is for both together. So I put it them in one parenthesis, and that's why it means u should be multiplied with all, or both of them here.
I think maybe a bit further down, like on the last one, there's two parentheses. There's t minus 1, u, t minus 1.
Okay,
Does that mean that
this
it's
is for the
multiplied?
first f part, and this is for u part. You know, in this shape, you have one f part and one u part. So
Okay.
the first one is for the first portion parenthesis, and another one is for here.
Oh, yes.
And then here, we don't do the multiplication anymore. We just leave it as it is, because it is in the shape we want to have. Yes?
Is it always possible to like get the same in the parentheses as
It is possible, but as I said, you have to find the way to do that. After this example, I have another example, which is one of the exam questions. I made it maybe in fall 21 or fall 22. So I want that give you that one to try it yourself here, such that you can see how you should do this conversion, or make sure that they are the same. Okay. Any other questions so far? Yes, please.
So the t minus a variable only have to match between terms, right?
The term you have outside of u always should have the same format as what you have inside this parenthesis for u.
Yeah, but then you have the plus, and then it's free, so I can match it with a different number afterwards.
Can you repeat it again?
So you only have to match the variable between terms. So you have the plus that divides them, then you can have a new variable that matches within the parentheses.
I can follow or get what you mean exactly.
So in the first term you have the minus 1, and in the second term you have the minus 3.
Yeah, but this, you mean here and here, am I right?
Yeah.
Okay, but you know, we look at this as one case, and this is another case.
Yeah, so it's just like the
Two different.
the plus and the minus divided.
Yeah, yeah.
Okay.
This plus and minus, it means that you have to add them or subtract.
Yeah, exactly.
Because your function is a combination of these all intervals, so you have to do this.
It's just the way you have to match them.
Yeah.
So is it because of the linearity? So you can look at them as different
Yeah.
functions.
Yeah.
Thinking about the second last line, where you have minus 2 multiplied, above, I mean, minus, yeah, minus 2 multiply, this one.
Okay.
If you multiply it, it will be minus 2t.
But we don't do
Plus-
that. We don't do that because if you do the multiplication here,
Yeah.
then what you have outside here, or maybe if you do it here, what you have here is not the same as in parentheses you have here. The point is that you have to always rewrite in a way that whatever is outside of the u have the same format of in parentheses in front of you. So yes, mathematically I can do the multiplication. They are the same, but then you cannot use the rule directly.
Yeah, that's why I'm asking, because it will not give me t minus 5 minus 2. As you bring it from the, from here.
Okay.
But you will, when you multiply it, it will give me minus 2 plus 6.
Okay, let's see if I can go back there. Here I have, I just want to show it here. So I have minus 2t minus 6, which is minus t plus 6. Am I right?
Yeah.
And then I have another term here. For sure it gives the other one, but let me show how I can prove it to you.
You're missing 2t. Just when you did it, the minus 2t minus 6, that's gotta be minus.
The other board.
Yeah, the other board. yeah, you're missing it. In the parentheses, you have 1t plus 6 in the board downstairs.
I know,
This
here.
one, it has to be 2t, right?
Oh, yes, yes, it should be 2t. Okay. Let me show you another way. So we have t minus 3 to the power of 2 u of t minus 3 minus 2 of. I want to prove that if I start here, I can go and reach the purple one. Then hopefully it's clear for you that they are the same. So what I do, I make the factorization of u of t minus 3. Then I have t minus 3 to the power of 2 minus 2 times t minus 3. And now I open this, it will become t2 minus or plus 9 minus 6t minus 2t plus 6. Am I right? Or did I miss anything?
Maybe you can factorize.
No, I just did the power of 2. So t2 plus 9 minus 60 is correct. Then minus 2t plus 6. Then it will become t2 9 plus 6 is 15. Yes, and then minus 8t. Okay? And then, now, if you do the multiplication of these two together, you get exactly this. So, they are the same. Okay. Can I go to the next step now? Good. So I need the next four. Now, I have my f of t in a format I would like to have it. And now I want to take the Laplace for each individual and then add them together. So this is board number 8. So I want to find the Laplace of f of t, which is capital F of s. Again, due to the linearity property of Laplace, what I can do, I can take or obtain the Laplace of each individual and then add them together. This is the linearity property. So this is what I do. First, I obtain the Laplace of t times u of t. This is in a table 7.2. And I think it's become 1 over S2 if you use table. So it's not difficult. Then I have my Laplace of minus t minus 1 u of t minus 1. This minus can come out of Laplace again, because its number is minus 1. Now I want to find this. Let's look at the shifting, second shift theorem. I have t with 1 unit shifting here and here. So are we agreed that I can use what I obtained for a previous term and then use this rule and write it as a e to the power of minus t0 is 1 times s, am I right? Yes. Then capital F of s, which in this case is s to the power of 2. Because for f, here you have t times u of t, which is 1 over s2. So you know capital F of s from here. So e to the power of minus t0, which in this case is 1. And of course, I should have a minus here as well. Sorry, I forgot the minus. Okay. Yes?
The T0 was minus 1, yes?
T0 is 1.
Oh, okay.
T minus 1. You can see T minus T0. I have T minus 1. So T0 is 1.
Okay, now I see.
just go through it? Why you're ending up with the big F of capital F of S? Why it becomes 1 over S squared?
Okay, so here you have t minus 1, u of t minus 1. This is with one shifting. If I want to remove the shifting from this, it is t times u of t. So this is your f, I mean it's this one, without shifting, and this is this one with shifting. And for this, in this particular example, you had it from before, and if you have an example which the not shifted one is not in your computation, you can find it in maybe tables. But here I had it here, so I could directly use it. Is it clear? Perfect. Now I have another term, this one. But you know, because I prefer to continue with this, because this is the second power of this one. So I will go with this one first. So I have the Laplace of minus 2 u of t minus 3. No, sorry, I write it wrong. T minus 3 u of t minus 3. And again, minus 2 is a number. I bring it out. Now for this one, I can use the same rule as above. So it's not very difficult. So minus 2, because I have it here, e to the power of. Now the shifting is 3 units. So my t0 is 3. So minus 3t 1 over s2. Yes, please?
Isn't it minus 3 s?
Oh, yes, should be s. Thank you. Or maybe I should write it. S. Yes. Okay. Now, I want to go to this one. I want to find the Laplace of t minus 3 to the power of 2 u of t minus 3. For this one,
But haven't you already figured it out?
no, I already, the one which we did is this term.
Okay.
Yeah, and now I went back to this one.
Okay.
The reason which I jumped over this one, because this was very similar to the second part, then I wanted to show they are the same, so we can follow the same rule. That's why. Now I'm back here. So here again, this is with shifting. We remove the shifting, then your f of t will be t to the power of 2 times u of t. So this is this. From this one, I want to make the top one, the Laplace of it. So I will find the Laplace of this here. Again, you can use tables, and if you do it correctly, it is 2 over s to the power of 3. So your capital F of s, this one, for here, is equals to 2 over s3. Now I have with minus or 3 shifting, so it will become e to the power of minus 3s times 2 over s3. Let me check if I did it correctly. Yes.
Isn't it minus?
Why minus?
Oh, no, sorry.
Okay.
Never mind.
Now we have the last one. So we have the Laplace of minus t minus 4 to the power of 2 u of t minus 4. Again, this minus is a number. I bring it out. So it will become minus. This format is very similar to what we had before with only 4 unit shifting. So e to the power of minus 4s 2 s to the power of 3. Yeah, sorry, I don't have a space though. So now I have the Laplace for all. So the only thing we need to do to finish the example is write that f of s is the summation of all I have here. So it is 1 over s to the power of 2. Then minus e to the power of minus s 1 over s2. Then minus 2 into the power of minus 3s 1 over s2. And then plus into the power of minus 3s times 2 over s3. And then minus, again, e to the power of minus 4s times 2 s3. And I think you can find all of the solution also here. If you want, you can take a picture if you want.
Is there a reason why you are writing S3 in the
In the denominator.
denominator? Yeah.
Actually, just a second. Are you done with the pictures?
No.
I don't think you need my
Thank
pictures.
you.
I'll wait.
Could you move more to the...
Okay. You know,
You're standing in the middle. Okay, there. Thank you.
okay. This s to the power of 3 comes from here. And that's why I write it. Because for t2 u of t without any shifting, the Laplace would be always this. So my capital F of s for these two are 2 over s3 and 2 over s3. And that's why I have it there and here.
But shouldn't it be S4?
No, and actually let's show you the table why it is S3. I have the table open somewhere here. It is in a table here. Where is it?
Number 4.
Yeah, here. If n is 2, and then as you know, I told you last time, we have a hidden u of t in front. Then I go here, so it will become 2 at the top, and then s to the power of 2 plus 1, which is s to the power of 3. So if I use this rule, then you have 2 over s3, and that's why it is s3. Now,
What is shifting when you speak about
shifting. Okay, let me show it here. Can you remember before the break we had the function u of t, which was here, this orange one, and I said that you can have any function like unit step with the shifting, for instance, with the t0 shifting to the right when t0 is greater than 0. It means that you implement your signal or your function with the t0 unit delay. So your new or the blue one would be u of t minus t0 shifting. Or in reality, when you implement a signal with the t0 second delay to the system, then it means that you have this shifting. So shifting means delay in reality, in a real application, when you implement a signal to the system. So here you have a unit step with t0 shifting. You can see instead of starting at the origin, your signal starts at t0.
Ah, so you like push it.
Push it or shift or implement with a delay.
Okay.
Yeah.
Tættere stikkontakt. Tættere stikkontakt. Tænder en stikkontakt. Klokken et eller andet.
Okay.
Nå, så glem det.
I have example number 3. This was one of the exam questions a few years ago. So I give you 10 minutes time. So you try it yourself first, and then we solve it here. So first, we have this piecewise function, which is the cosine of t for the range of 0 to pi and 0 elsewhere. So you need to plot it, but you can skip the plot here because it's not an exam. But rewrite your function with the Heaviside function or unit step function. And then when you did it, determine the Laplace transformation, capital F of S of your f of t.